Hello everyone and welcome to this optional video. We're going to see some integrals with branch cuts today. That means whenever you have a multivalued function and that multivalued function comes with some other functions as well, and then you want to integrate over this multivalued function, that's the thing that we're going to see today. So this integral that you can see over here is a contour integral, and this integral will involve some branch cut and branch points. So before I get started, let me tell you that dealing with branch cuts and branch points actually involves that what kind of multivalued functions you are dealing with. And according to the function, you have to choose a suitable branch cut. Then you can proceed to integrate. Okay? So the reason I'm choosing this integral will be apparent at the end of the video. But for now, let's consider this integral around some keyhole contour. So let me just write down the name of the contour. It's called a keyhole contour. And I'm going to draw the contour so that you can see that what do I mean by a keyhole contour and all that. So let me go down a bit. So let's try to draw the real and the imaginary axis first. So I'm gonna go with a dot 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 for the real axis. The reason will be apparent very soon. And to evaluate this integral, we're going to choose a contour that looks something like this. Let me go to another color. Now, it really looks bad because the drawing is not pretty good. And this is the origin, that is the zero thing. And since we have two poles at z is equals to minus and z is equals to minus b, where a and b, both of them are greater than 0, we can mark them over here. So let's say this is minus a and this is minus b. Or it can be vice versa, but it doesn't matter. So let's try to indicate our lines. That means how we are going to enclose the contour. So we're going to start from here, and this is actually a semicircle, though it doesn't look like one, but it's actually a semicircle. And let's say this semicircle has a radius epsilon, and this semicircle is denoted by c underscore epsilon. And let's say this whole circle type of thing, which is not a complete circle, it has a radius of capital R. And this part, that means this guy over here, I'm going to indicate with them with arrows. This is, let's say this is written as C of R. This is another contour, and then there are these two lines. So since the smaller circle type of thing, or a semicircle, whatever you want to call it, it has a radius epsilon, this point is actually epsilon, and let's say this point is R. Alright, and we're going to start from here. We'll go up to R, then we will revolve around this contour, that is CR, and then we'll go like this. And here, when we come over here, then we're going to move like this. So these arrows indicate how we're going to revolve around the contour. Now, if you recall that log of z or ln of z is actually a multivalued function, and this is origin or 0. This point is a branch point of the logarithmic function, and since it is a multivalued function, we cannot do a 2pi rotation in the z plane. Alright, so that's why we need to introduce a branch cut. So the branch cut for this integral we will choose is something that starts from 0, and since infinity is also a branch point, we're going to choose a branch cut that goes from or extends from 0 to infinity. And let me just use a thicker color, and this is our branch cut. So recall that branch cut actually tells us that not to cross this line over here. That means we are not allowed to go past this line, and that's why we have to go around. We have to move in another arc, and then finally we come to the epsilon point. Alright, so this is the setup to evaluate the integral. Now let's try to evaluate it. So our integral was something like this: log of z dz by z plus a z plus b. And if you notice that we have actually one, let's say this is one, this is the second path, this a bigger circle, this is the third path, that is from here to here, and this is the fourth path, that means c of epsilon, right? We have 4 parts. So at first we go from epsilon to r, and we go along this line like this in the positive x-axis, right? At this point, at this direction, the numbers, or in the complex plane, all the points that in that lie in this direction can be parameterized as z is equals to x, since there is no imaginary component. So we write log of x dx x plus a x plus b. Now what I'm going to do is that I'm going to consider the line number 3. Why? It will be apparent a bit later, because I'm not going to write explicitly the terms for this smaller circle over here. Let me just highlight it with this color that is appearing over here, and this one is appearing over here. I'm not going to write it explicitly, and that reason will be coming from a theorem, because this the contour integral on this part and this part, that means these two circles with c epsilon and cr, they will actually go to 0. So that's why I'm not writing them down explicitly. I will, but not in this manner. So when you go from here, let's say this is point A and this is point B, and again this B has this epsilon thing, right? Because it starts from over here, and this has a coordinate of epsilon, and this has a coordinate of r. So I'm in the point A. So you are starting from r and you are going back to epsilon point. So the lower limit is now r, the upper limit is now epsilon. However, now you are going in the opposite direction. That means if you zoom this area in like this area is actually, the upper part goes like this. So that's why z is equals to x over here. However, when you go back like this, you are actually having the z as x e to the power 2 pi I. Why, you may ask at this point? Because if you notice, we started from epsilon, we went to r, but then we made a almost 2 pi rotation. Almost. Not exactly, but almost. So that's why approximately you can say that this is just x e to the power 2 pi I. That means you are going along the reverse direction like this. Okay? This line and this line, they will have a phase difference of 2 pi e to the power 2 pi I. So that's why there is this 2 pi I coming. Okay? Because any complex number can be written as r e to the power I theta. You do not cross the 2 pi barrier, but you are almost very close to 2 pi. So that's why you write e to the power 2 pi I. That's the reason. So instead of z, now you write log of x e to the power 2 pi I. Now you may ask, why am I not using the fact that e to the power 2 pi I is equals to 1? Well, because you see there is a logarithm over here. That's why I'm not using e to the power 2 pi I equals to 1 over here, because that will spoil our multivaluedness thing. Since this is a multivalued function, we need to be very careful at what we do. And in the denominator there is no log, so that's why you can directly write x plus a and x plus b by using the fact that e to the power 2 pi I is equals to 1. Now I have to write out the rest of the things, and let's write it in a very shortcut manner. C of r and C of epsilon, and this will be our f of z, that means this log of z divided by z of a times z of b. So let me write that down. So this CR and C epsilon are just contributions coming from the bigger circle and the smaller circle. So now, before I proceed, I want to make use of the theorems that you already know. So let me just recall one of the theorems that, let's say this is theorem 1, and it says that if on a circular arc, that means this CR on this circular arc of radius r that is centered at z is equals to 0, centered at z is equals to 0, if z times f of z goes to 0 uniformly as r goes to infinity, then limit of r goes to infinity, C of r, that means the circular arc, this thing is 0. So using this theorem, you can easily show that this guy, that means this integrand multiplied with z, when z goes to 0, will actually be uniformly 0. Alright, and I want to use another theorem that tells me, obviously you have also seen this theorem in a very informal manner, but it's nonetheless important. And this theorem tells us that suppose on the C epsilon thing, that means the smaller circle over here, you have z minus z naught or times f of z that goes to 0 uniformly. This z naught is a singularity, by the way, so keep that in mind. Or so to say, this z naught is a point that this smaller circle encloses. So in our case, this is just 0. And obviously, z is equals to 0 is a singular point, because you see that log of 0 is not defined, right? So what I was saying was that if this condition is satisfied, that means up to this, that on this C epsilon contour, z minus z naught times f of z, if that goes to 0 uniformly as epsilon goes to 0, that means the radius of the circle is shrinking down, then limit epsilon goes to 0, C of epsilon, f of z dz is equals to 0. And using this, you can also show that this part is 0 by theorem 2. And this part is also 0 by theorem 1. So that's pretty convenient. Now we need to only deal with this guy and this guy. So let's write them down. And now we're going to do a trick that will save us a lot of time, because you see that this has this r epsilon thing, and at first epsilon is the lower limit and r is the upper limit, and here we have this r epsilon, but the limit is now reversed. So what we can do, we can pick up a minus sign and we can just reverse the limit that was given before, and now we can write log of x e to the power 2 pi I as log of x plus log of e to the power 2 pi I. And now you know the difference, that instead of writing e to the power 2 pi I equals to 1 in the first place, now we are going to write it like this. And if you evaluate this thing, this is just e to the power 2 pi I. So that's why we didn't use the identity to the power 2 pi I is equals to 1 in the first place. So let me write it like this, 2 pi I, and obviously put a bracket over here because the minus sign is outside, and use x plus a, x plus b. Now what we're going to do, we are going to take r goes to infinity and epsilon goes to 0. And the reason will be apparent very soon. Why am I doing this? It will actually give us some other integral that we need to evaluate. I didn't show it at first, but I rather wanted to start from the contour integral and then show you that what does this contour integral gives you at the end of the day. So if you do that, this will be 0, infinity, log of x plus a, x plus b, then you have a minus, and you can break down this integral because there is a plus b format over here, and in the denominator there is these factors, and there is a minus sign like this, and after taking those limits, this will be log of x, x plus a, x plus b, then finally you have another minus, that is the, oh yes, there should be a dx. I'm missing all the dx for some weird reason, so let's just give a big dx over here and enclose this thing with third bracket. So now you have a 2 pi I and finally a dx divided by x plus a and x plus b, right? After taking the limit that epsilon goes to 0 and r goes to infinity. And now you see that these two parts cancel each other out. So ultimately you have 2 pi I 0 to infinity dx x plus a x plus b. And on the left hand side, this was just log of z dz and z plus a, z plus b. Oops, I forgot a dz as well. But due to Cauchy's residue theorem, on the left hand side you can write this as 2 pi I sum over the residues, right? And on the right hand side you have this 2 pi I integration of 0 to infinity d of x, x plus a, x plus b. So this 2 pi I and this 2 pi I will cancel out, and all you have left is 0 to infinity dx x plus a, x plus b is equals to minus sum over the residues. And these residues are coming from the singular points. That means it is coming from z is equals to minus a and z is equals to minus b, right? Now we just need to find out the residue. And this is the integral that this contour integral we considered will give us at the end of the day when we take the limits appropriately. So again, let's look at our function to calculate the residues. One of the residues occurs at z is equals to minus a and one of them occurs at z is equals to minus b. And if you look at our contour, you can see that a and b, both of them are inside the contour, right? So let's try to calculate the residues. So sum of the residues means residue at z is equals to minus a and then residue at z is equals to minus b, right? So this is just log of minus a and there will be a minus b. You have to calculate it. I'm skipping the steps. And here you'll have log of, sorry, modulus minus b. Or you can not choose to write a modulus since you're doing this complex variable thing. So it's up to you. And you will have minus b minus a, minus b minus a. Sorry, it shouldn't be minus b minus a, my bad. It should be b minus a. Now if you just simplify all this, that means instead of log of minus a, you write it as log of a plus I pi, because this is a real number but it's lying on the negative line. So the argument, I mean the principal argument is pi, and you have to recognize the fact that we are also working in the principal branch. This thick red mark denotes the principal branch. So that's why we write it as log, or you can write log whatever you want. So let me just write log a plus I pi, and here you will have a minus b, and finally you take a minus common like this and you have this a minus b thing, and you will have log b plus I pi. Okay, and if you just simplify this whole thing, this is just a minus b log of a by b, and this is your result. That if you integrate from 0 to infinity this guy, dx by x plus a, x plus b, this is your answer. As I was saying, in general, doing integrals with branch cuts is really difficult unless you have chosen a branch cut that is very suitable and pretty easy to do. Otherwise, it's pretty difficult. So this will be it for today, and thank you.